All right, so we have a couple of short topics to cover today before we get into the review session. The first of which is voltage regulation of a transformer. So voltage regulation is a measure of how well a transformer maintains its secondary voltage under a changing load. So effectively, if we had a transformer whose, let's say it was a step-down transformer, whose low voltage side was rated for 240 volts RMS, realistically, we want that secondary voltage to be somewhere close to 240 volts RMS at all times, at least in power distribution applications. And so the voltage regulation is a figure of merit that tells us how much variance we should expect to see in that secondary voltage as we apply different loads, ranging all the way from a no load condition where it is completely open circuited up to a fully loaded condition where the secondary windings are drawing rated current. Okay. So mathematically, our voltage regulation is defined as follows. The percent voltage regulation is equal to the magnitude of our voltage under no load conditions minus the magnitude of our secondary voltage under full load conditions divided by the magnitude of our secondary voltage under full load conditions. And then we simply multiply this by 100%. So we are going to be able to define the magnitude of the secondary voltage under no load conditions and under full load conditions and put it in terms of things that we either know how to measure or know how to find, okay? So under full load conditions, the secondary windings should be supplying or providing rated voltage and current. So the magnitude of the secondary voltage under full load conditions is literally just the secondary rated voltage, right? So whenever we have a transformer that's say 7200 volts RMS / 240 volts RMS, if the secondary is the low voltage side, then our rated voltage is 240 volts. If the secondary is the high voltage side, then our rated voltage would be 7200 volts. It's what we're specifically told. So that's the easy one, right? Under no load conditions, it's a little bit more difficult. So under no load conditions with all impedances referred to the secondary side, Our transformer equivalent circuit looks something like this. Back here, so I can have a picture of it. So here we have A times V1 A squared RC JA squared XM This is the equivalent resistance of our secondary side, the equivalent reactance of our secondary side. And then this is our voltage V2. So this voltage way over here on the left is actually V2 under no load conditions. So we can say that V2 under no load conditions is just going to be this open circuited V2, which is actually just the rated voltage, plus whatever I2 is, times the equivalent resistance of the secondary and, the equivalent reactance of the secondary. So now that we have these two quantities defined, let's work an example and put this into application, okay? So let's say that we have a 100 kilovolt ampere rated, 7,200 to 240 volt RMS, 60 hertz transformer is tested, and the collected test data is provided below. So our open circuit test was performed on the high voltage side, and our voltmeter reading was VOC is equal to 7,200 volts RMS. Our ammeter reading was IOC is equal to 0.65 amps RMS. And our wattmeter reading is our open circuit power losses are 425 watts. And then our short circuit test was also applied on the high voltage side. And our short circuit voltage from our voltmeter reading is 250 volts. Our short circuit current, which is just rated current, is 13.889 amps RMS. And our short circuit power losses are 1,420 watts. The transformer is connected to a full load which operates at a power factor of PF is equal to 0.90 lagging. And I want us to determine the percent voltage regulation of the transformer. So I'm going to scroll up here really quickly. And I want us to look for the different pieces of information that we are going to need, okay, in order to determine our percent voltage regulation. So we're going to need the rated voltage of the secondary, which means we kind of have to decide which side is the secondary for our case. We are going to need to know the current flowing through the secondary, so that's going to take a little bit of effort. We are also going to need to know the equivalent resistance referred to the secondary side, as well as the equivalent reactance referred to the secondary side. So these two are the series components of our transformer equivalent circuit model. Okay. All right, so do we want our primary side to be the high voltage or the low voltage? High voltage, okay? So let's say down here that our high voltage is our primary and our low voltage is our secondary. Taking these two pieces of information into account, our turns ratio is going to be the ratio of the low voltage to the high voltage, or 240 volts RMS over 7,200 volts RMS, which is going to be 1/30. We're going to wind up using that turns ratio in order to refer our impedances to the low voltage side, because we need things on the secondary, and all of our test results are going to give us things on the primary or the high voltage side. Okay? All right, so let's knock off one low-hanging fruit thing here really quickly. What is the magnitude of our rated secondary voltage? 240 volts RMS, absolutely. Literally given to us, we don't have to do any more work for it. So that's one piece of information done, okay? Now we've got 3 other things to figure out, okay? So let's work on our resistance and reactance next, because we actually need to know those before we can really figure out our current or anything, okay? So the equivalent resistance on the high voltage side is going to be our short circuit power divided by the magnitude of our short circuit current squared. So this is going to be 1,420 watts divided by 13.889 amperes RMS squared. And this comes out to be 7.361 ohms. This is our high voltage. This is the resistance referred to the high voltage side. So on the low voltage or the secondary side, should we divide by A squared or multiply by A squared? So we're going from the primary side to the secondary side, so we should be multiplying by A squared. So REQS is just going to be REQ high voltage times A squared. So that's 7.361 ohms times 1/30 quantity squared. And I got 8.179 milliohms. For our equivalent reactance on the high voltage side, that is the square root of the magnitude of our short circuit voltage divided by the magnitude of our short circuit current, quantity squared, minus the equivalent resistance on the high voltage side squared. So that's going to look like 250 volts RMS divided by 13.889 amps RMS, that quantity squared, minus 7.361 ohms quantity squared. We take the square root of that whole thing. And this comes out to be 16.426 ohms. Referring that to the secondary, we're going to multiply that quantity by A squared again. So XEQ on the secondary side is just XEQ on the high voltage side times A squared, or 16.426 ohms times quantity 1/30 squared. And that comes out to be 18.251 milliohms. And so now we need to figure out our current. So let me go back here really quickly to our equivalent circuit, because we've got to figure out how to solve for this quantity I2 under full load conditions. So I'm looking at our equivalent circuit here, and all I'm adding is some impedance, okay? So since we're under full load conditions, we know that our impedance is absorbing an apparent power of 100 kVA, because that's what we're rated for, right? We also know that the magnitude of our load voltage under full load conditions is 240 volts RMS. So what should our current be? Okay. So the magnitude of I2 is just going to be that rated apparent power divided by our rated voltage, 100 kilovolt amperes divided by 240 volts RMS comes out to be 1,250 over 3 amps RMS, or 416.667 amps. Now, if we look at our equation up here, we don't need just the magnitude though. We need that real full current. So we also have to figure out what the phase angle is. Anybody have any thoughts on how we might determine the phase angle of our current based on the information that we've been provided? Power factor, absolutely right. So our power factor angle, theta S, which is the inverse cosine of our power factor, is by definition theta V minus theta I, and theta I is the thing that we're trying to solve for. So we are going to make an assumption here. We are going to assume that theta V is equal to 0 volts. So we're just saying our point of reference is 0 volts on the voltage, and then whatever the current is going to be something with respect to that reference, right? So it really doesn't matter that we assume theta V is equal to 0 volts, because we know that theta I is just going to be however many degrees different from whatever we assume it to be, okay? So putting this together, we can say that theta I is effectively equal to negative theta S, or negative the inverse cosine of our power factor. So theta I will be negative the inverse cosine of 0.9 lagging. And that's going to come out to be negative 25.842 degrees. And from this, I2 is 416.667 angle negative 25.482 degrees amps RMS. Therefore, V2 under no load is V2 rated plus I2 times REQ plus J XEQ. So that is 240 angle 0 degrees volts RMS plus 416.667 angle negative 25.482 degrees amps RMS times 8.179 plus J 18.251 milliohms, which comes out to be 246.440 with an angle of positive 1.246 degrees volts RMS. From this, our percent voltage regulation is the magnitude of that voltage, so 246.440 volts RMS minus our rated voltage of 240 volts RMS divided by our rated voltage of 240 volts RMS times 100%, and this comes out to be 2.683%. So this particular transformer does a pretty good job of voltage regulation. Yes, sir. Thank you. Yep, you're 100% right. So it should have been inverse cosine of 0.9. Thank you for that, Avery. Yes.
Also, is the angle for theta I, is it 25.842 or is it 25.4?
842. Thank you for that. Just transpose those numbers. Got in a hurry. 842. Thank you. All right, so 2.683% voltage regulation. This particular transformer does a pretty good job. Really, anything under 3% is acceptable for power and distribution transformers. There are some applications, however, that really require very, very poor levels of voltage regulation. How many of you guys have any experience with arc welding or anything like that? Few of you have done that kind of stuff, probably at internships, working at a shop in high school, something like that. So for an arc welder, it takes a very, very high amount of voltage in order to establish your cutting beam. And then once it's established, it actually only requires a very small amount of voltage to maintain it. So a transformer in arc welder is usually one that's designed for bad or poor voltage regulation, so that the voltage at the secondary drops down low so that you're not just wasting power converting it into heat, because you don't need that high voltage. Same thing for discharge lamps and all that kind of stuff. So there is a practical place for transformers with low voltage regulation. It just is not in power distribution. Okay. All right, so our last little topic that we're going to cover is transformer efficiency. All right, so the efficiency of a transformer is defined as the ratio of the output power P out to the input power P in, or eta, Greek fancy looking N, is equal to P out divided by P in. So our input power is just going to be the output power plus any losses that we incur, okay? So we can write this as P out divided by P out plus P losses. Well, what kind of losses do we know about that transformers regularly experience? So we have copper losses, or I squared R losses, due to the resistance of our windings. And then we also have core losses because we lose energy constantly magnetizing and demagnetizing our core, right? So our last relationship here is going to be P out divided by P out plus, let's put P core here, plus P copper here. Well, our core losses are literally what's measured by the wattmeter in the open circuit test. And our copper losses is literally what's measured by the wattmeter during, I don't know why my screen is scrolling on me like that, our short circuit test. So this is all information that's regularly provided to us during the transformer testing process. Okay. So because the output power is the average power delivered to the load, we can re-express this as our rated apparent power times the power factor at which the load connected to the transformer is operating at, divided by that same rated parent power. This is assuming we're at full load, times power factor plus POC plus PSC. So if we wanted to determine the efficiency of the transformer from our previous example, that would be 100 kilovolt amperes times 0.9 divided by 100 kilovolt amperes times 0.9 plus 425 watts for POC plus, let's scroll back up here, 1420 watts for PSC. And this comes out to be about 97.991%. So practical transformers are actually very highly efficient. They're designed to be. All right, so that's the last new material that I wanted to talk about. So now it's time for review. So what are we reviewing? Power. Like, what do you mean by power? Complex, apparent, average, reactive, all of the above, none of the above? Most of what we did before break would be something dealing with. So when you say most, related to magnetic circuits or related to transformers?
What's gonna be on the test?
Magnetic circuits and transformers. So effectively, I'm making your test. I have not made it yet, but I'm making your test by picking out one medium difficulty problem from each of the 4 homework sets and then changing the numbers. So if you have been able to do all of the homeworks and get the correct answers, after I actually put the correct answers on there, then you're good to go. Including the homework that, just got uploaded, but is due on Tuesday so that you do it before the test, Sure. Yeah.
Something like this, and then we just like change the numbers or something.
Well, why bother changing the numbers? All right, so for this one in particular, actually, I need the handout as well, but I can write this down and we can run through it quickly, okay? So yes, actually, that's not the one with my material, but I can pull it up on the computer. So the problem that Avery handed me is a magnetic circuit problem, where, let me draw this out. We have core. That looks something like this. Let's see, our coil is over here. And our coil has 100 turns. This distance is 5 centimeters. This distance is 15 centimeters. This distance is 10 centimeters, so this is very obviously not drawn to scale. Fifteen centimeters. Another 5 centimeters. 5 centimeters. 15 centimeters. 5 centimeters. And our gap is 0.02 centimeters. The thickness is 2.5 centimeters. The stacking factor is 0.92, and we're told that it's made of my made-up material, Hartmanium. And we are trying to find the amplitude of the required coil current, I max, in order to achieve a magnetic flux density of B max is equal to 1.1 Tesla in the middle leg of the core. All right, so the first thing that I'm going to do is I'm going to pull up my table, which is going to take me a moment to find it. Or it's not a table, it's a plot. I think it would have been here. Assignment sheet, nope, not that one. Hmm. Sorry, it'll take me a second to find this file. Let me see if I put it on Canvas. I know exactly what it looks like, I just don't know where I randomly saved it. This is. Okay. Cool. There we go. Yeah, thank you. You're right. How do I make this bigger? Actually, if it's the last page of the homework, I'll pull it up here. Thank you for that, Lance. open the folder, don't rename the, oh my God, it's pissing me off. All right. Sorry that took so long. Okay, so we're looking at hartmanium with a magnetic flux density of 1.1 Tesla. Hartmanium is the blue curve. 1.1 Tesla would be right about here. So now we're just going to go down. So let's say that our H field is about 250 amp turns. Okay. So this corresponds to H in the core is about 250 amp turns, which means the permeability of our core is, let's see, B is equal to mu H. So H over B. Yep, B over H. So 1.1 Tesla divided by 250 amp turns is 11 over 2500 or 4.4 times 10 to the minus 3. So let's see, Tesla per amp turns, where turns isn't going to matter. And now we need to make sure that this is in the units that we're used to working with. So let's play around with this really quickly. Okay. So mu C is 4.4 times 10 to the minus 3. A Tesla is a Weber per meter squared. And that's going to be over 1 amp turns. Well, a Weber is a amp second per volt. No, hold on. A Weber is a volt second. And a volt second per ampere is a Henry. That's where we're going for, right? So let's put this as, let's see, 1 Henry divided by a volt second amp. So the volts and the seconds cancel here and here, the amps cancel here and here. So I have Henrys per meter squared. It's usually in centimeters. Yeah, I'm trying to figure out if I'm missing a unit of length somewhere. Let me go back really quickly here because it's been about a month since I worked one of these. Let's see.
I have to thank the class that I remember when I came to visit this year, I had to use for
Yeah, I'm just trying to figure out where. Yeah, because a Tesla is a Weber per meter squared. By definition. So where am I missing? Where's my length thing? Where's it gone away to? It's the unit thing that I want to make sure that I get right because it's going to mess up stuff if I don't. So I just want to double check through things here. So a Tesla is a Weber per meter squared. I have Webers per meter squared. I know that a Weber is a volt second. I know that a Henry is a volt second per amp. I bet my magnetizing force is supposed to be amp turns per meter, but let me look at the units for H field really quickly just to make sure. Yep, H is usually measured in amps per meter, so that's the issue. So this should be amp turns per meter, and I'll need to update that chart, which is going to put a meter up here. And then that meter cancels out one of those meter squares, and I'm going to be left with Henrys per meter. Now I'm going to multiply this by 1 meter is 100 centimeters. And so that will give me
Per meter squared meter per amp turn. And then you canceled out the meters, so you have Webers over meter amp turns. And then, so a Henry is a Weber per amp turn.
Correct.
So it's Henry over meters, and then you just move the decimal over 2 places, so it's Henry per centimeter.
Yep, that's what I'm getting, Henry per centimeter. Yeah, so 4.4 times 10 to the minus 5. Yep. Henrys per centimeter in the units that we're looking for. Yeah. So I do need to update that chart to express the magnetizing force as amp turns per meter. So I'll need to make a note to do that. All right. So mu C is done. So now we need to, let's see, think about things here. We're trying to figure out what current is flowing into coil to cause that B field. So realistically, we also need to know what the flux through that middle leg is because we're trying to figure out effectively what current is causing that particular flux, okay? So the flux through the middle leg is going to be equal to the B field times the area of the middle leg. So while we're working on that, let's figure out what that area is going to be. And this is where we're going to incorporate our stacking factor and all that kind of stuff as well. So the area of our middle leg looks to be 10 centimeters times 2.5 centimeters. Times our stacking factor of 0.92. Is 23 centimeters squared. And so that's going to be 1.1 Tesla times 23 centimeters squared. So let's see, I need 1 meter per 100 centimeters, that thing squared to give me a flux that's just in Webers, right? So that conversion factor there is to get into account that a Tesla is a Weber per meter squared, and my area is measured in centimeters squared. So 1.1 times 23 times 1/100 squared comes out to be 2.53 times 10 to the minus 3. So 2.53 milliwebers. Okay. And now we're getting into our magnetic circuit relationship type thing, right? So just to mainly remind myself at this point, I know that Ni is equal to flux times reluctance, right? That's my Ohm's law for magnetic circuits. I'm solving for I. So that's just going to be my flux times my reluctance divided by the number of turns. So that's what I'm aiming for here. Trying to piece together what I'm trying to find. All right, let me draw my magnetic circuit. So I believe my magnetic circuit is going to look something like this. So this is going to be the reluctance of my gap. I'm going to get rid of this guy right here and just short it out. And so this is going to be the reluctance of my middle leg minus the gap. This is going to be the reluctance of the top left portion, the top right portion, the right leg, the left leg, the bottom left, and the bottom right. And based on the cross-sectional areas and all of that kind of stuff, I know that the reluctance of the top left is equal to the reluctance of the top right, is equal to the reluctance of the bottom left, is equal to the reluctance of the bottom right. I know the reluctance of the left leg is equal to the reluctance of the right leg. And so it looks like I'm only going to have to solve for 4 different reluctances here to figure out what's going on, right? The middle leg will have its own thing because it's got its own cross-sectional area. The gap will have its own thing. All right. Okie dokie. So let's work on the top left thing first. So that is going to be, I'm going to cheat and look at one of my older things because it's been a minute. So I want the length of the top left portion. So that's going to be from here to here. So what should that length be? Yep, 2.5 plus 15 plus 5. So 22.5 centimeters. All right. this is going to be divided by my core permeability. So 4.4 times 10 to the minus 5. Henries per centimeter. And then I'm going to have my core area. So that's going to be my width times my thickness times my stacking factor. So my width is 5 centimeters. My thickness is 2.5 centimeters. My stacking factor was 0.92. So I'm going to throw that in my calculator. 22.5 divided by 4.4 times 10 to the minus 5 times 5 times 2.5 times 0.92. I got 4.447 times 10 to the positive 4 amp turns per Weber. For my left leg, go back up here. I'm looking for this length, which to me is just going to be 15 plus 5. So that'll be 20 centimeters over effectively that same denominator. 4.4 times 10 to the minus 5 Henries per centimeter, 5 centimeter, 2.5 centimeter, 0.92 stacking factor. I believe that comes out to be 3.953 times 10 to the 4 amp turns per Weber. Now let's do the middle. So that's going to have a length of 20 centimeters minus the length of my gap, which was 0.02 centimeters. Divided by that 4.4 times 10 to the minus 5 Henries per centimeter. And then the area of the middle we already found to be 23 centimeters squared. If I'm remembering correctly, yep. So 20 minus 0.02 over 4.4 times 10 to the minus 5 times 23. 1.974 times 10 to the 4 amp turns per Weber. And then we have the gap. So 0.02 centimeters. 4 pi times 10 to the minus 9 Henries per centimeter. And then our width is 10.02 centimeters. And our thickness is 2.52 centimeters, because we increase the dimensions by the gap length in all directions. Just double check that that width is 10. Yep. So 0.02 over 4 pi times 10 to the minus 9, 10.02, 2.52, 6.303 times 10 to the 4 amp turns per Weber. All right, and now I'm going to wind up simplifying a couple of things because I feel like I'm going to have to do the old current division backwards kind of trick here to figure out what my current is, right? So here's my MMF. Here's a reluctance here. So this is going to be the left-hand portion plus the top left-hand portion plus the bottom left-hand portion. This guy right here is going to be the middle portion plus the gap. And this guy right here is the top right plus the right plus the bottom right. And we already found that our flux here was 2.53 milliweber. And we are trying to find flux through the left-hand pass, so the flux that's being generated by our MMF. Yes. Mhm. Right. So we're using mu naught because there's no core material there. And we don't have to worry about the stacking factor because we're not inside the core. Right. So it's just the dimensions of the air gap area, and then we add the length of the gap to each side or to each dimension. Yeah. So we should not be using mu c because this is not a region of the core. And we don't have to take into account the stacking factor because the air gap isn't made of laminated sheets of material. The core is. So that's why we're using those absolute dimensions. And then the general rule of thumb is to increase the dimensions of the gap, of the core in the gap area by the length of the gap to account for the fact that the field gets to fringe and spread out. Okay, so current division backwards. So phi mid would be whatever phi left is times R left plus R top left plus R bottom left divided by R left plus R top left plus R bottom left plus R mid plus R gap, right? So that's how I would find the middle if I knew the left and it was splitting. Where I'm using the relationship that since I only have, I'm finding how it splits between. No, that's. technically, mathematically, it's gonna give me the same number, but it's gonna bother me because by putting that in the current division equation or the flux division equation, I'm effectively saying that the flux is dividing about this path, and it's not, because all of it's flowing through that path. So realistically, this should actually be top right, right, and bottom right here. But the numerical answer was going to come out to be exactly the same, but I don't want to make you guys not remember how to do current division correctly. So from this, phi left is going to be phi mid times the reluctance of the top right plus the reluctance of the right plus the reluctance of the bottom right plus the reluctance of the middle plus the reluctance of the gap, all divided by R top right plus bottom right. So phi mid times two times 4.447 plus the right, which was the same as the left, so 3.953. Since all of these are multiplied by 10 to the fourth, I'm just going to throw that away because my denominator is also effectively multiplied by 10 to the fourth, so none of those times 10 to the fourths wind up mattering. Then I have my middle, 1.974. Then I have my gap, 6.303. Divided by twice, 4.447 plus 3.953. And this phi mid, we recall, is 2.53 times 10 to the minus 3. All right. 2.53 times 10 to the minus 3 times 2 times 4.447 plus 3.953 plus 1.974, so 303. All of that is times 2.4, 2 times 4.447 plus 3.953, close parentheses, 4.16 milliweber. My equivalent reluctance for the whole circuit seen by our MMF source is R top left plus bottom left in series with R mid plus R gap times R top right plus the right plus the bottom right. So effectively, I'm saying the left branch in series with the middle branch and the right branch in parallel. And I'm putting numbers in there. So let's see. 2 times 4.447 plus 3.953 plus 1.974 plus 6.303 times 2 times 4.447, 3.953. All right, 2 times 4.447 plus 3.953 plus fraction 1.974 plus 6.303. 2 times 4.447 plus 3.953. 1.4 plus 6. 17.881 times 10 to the 4 amp turns per Weber. And now going way back up here to this relationship. I know the flux of the left leg. I know the reluctance seen by the MMF. I know the number of turns. So the last thing I have to solve for is I. So I will be flux, the left, equivalent reluctance divided by N. So that is 4.16 milliwebers. My equivalent reluctance, 17.881 times 10 to the 4 amp turns per Weber. 100 turns. 4.16 times 10 to the minus 3. 17.881 times 10 to the 4 divided by 100. 7.438 amps, give or take a little bit of rounding error because I did this with the calculator, not MathCAD. That was wildly tedious. So as a exam problem, I think that's probably too much work to expect you guys to do that and 3 other problems. Avery, what up? What did I screw up?
No, you didn't screw up anything. I was just out of curiosity, like, okay, so you're basing like your REQ equation.
Sure.
Okay, so the REQ will write R cup on R right above that. Basically off of which side will.
Exact-
Left side, you right.
Exactly right. So effectively what I'm trying to do, since I'm solving for something related to the coil, which is the amount of current carried by the coil, my Ohm's law for magnetic circuits tells me Ni is equal to flux passing through the coil times the reluctance seen by the coil. So I had to look, what is the equivalent reluctance the coil sees in order to use that Ohm's law-like relationship.
Okay, so it's. the full-
So if the coil, yeah, so if the coil was here in the middle, then it would have been R mid plus R gap in series with the left-hand leg in parallel with the right-hand leg. If the coil were over here, it would have been the equivalent reluctance of the right-hand leg in series with the parallel combination of the left and the middle. Yep. All right. So what else are we going to talk about now that we've killed that 30-minute problem? Yes.
You explain part C on part C problem.
Homework 2, problem what? That's gotta be homework 3 then. For these magnetic circuits problems, there's definitely going to be a diagram, but for like a transformer problem where I'm asking you to calculate equivalent circuit parameters and all that kind of stuff, I'm just gonna give you the test data and the ratings. There's really no point in giving you a circuit because you're trying to find out what every part of the circuit is. So I would just give you a circuit with literally no numbers or anything on it. All right, so okay. So you're trying to find mutual inductance, right? So gonna have to think about this for a moment just because it's been a minute. So what this boils down to is going to be very similar to the example problems that we worked in class, where we're either going to have to find the amount of flux that's generated by coil 1 that passes through coil 2, or the amount of flux that's generated by coil 2 that passes through coil 1, because that's going to be key to us determining that mutual inductance. So let me just turn here in my notes to an example problem so that I don't suffer too much through this, and let's take a crack at this guy. I'm going to close this homework set out. Don't save. We have a ugly looking core, something like this. We have one coil on the left-hand leg, if I'm remembering correctly. Sorry, getting confused with all the windows I have open. So this is coil 1, and it has 500 turns. And then here we have coil 2 wrapped around in this way. And it has, I think, 300 turns. And let's go ahead and put all those dimensions on here while we're at it. So 100 centimeters in length total. Forty centimeters here. This is 10. This is 10. This guy is 15. LG1 is half a centimeter. LG2 is 0.3 centimeters. Our thickness is 8 centimeters. And our core permeability is 12,000 mu naught. Okay. So let's say for the sake of argument that we are trying to find the flux that's generated by coil 1 that's passing through coil 2, okay? So from a magnetic circuit perspective, our circuit's going to look something like this. So here's MMF1. This is the reluctance of the left-hand leg. Then we have this top left piece. Then we have this middle piece. Here we have our second gap. This is going to be our top right piece in series with our first gap. Here's our right leg. Here's our bottom left. Here is our bottom right. This is the flux that's leaving coil 1 because and this is the flux that's generated by or passing through coil 2 that's generated by coil 1 is I think the subscript notation. Doesn't particularly matter here, but it's generated by coil 1 passing through coil 2. Okay. All right. So we effectively need to figure out all of those reluctances and all of that kind of good stuff so that we can simplify things and make it mildly less horrifying. And then once we get all of those reluctances taken care of, then we can just run through a couple of algebraic steps to figure out what's going on. All right, so let's look at a couple of things here really quickly. So our top left section and our bottom left section and our bottom right section are all the same size and have the same area, so those are going to be the same. Our left leg and our right leg are going to be equal, and then everything else is its own separate thing. All right, so top left, the length is going to be this length right here. Might be slightly better if I draw it on this thing where things are drawn to scale. So we can figure it out. So what should that be? Yeah, so 50 is half of the total length minus half of the width of the left leg. So 50 minus 5 is 45. Okay. Then we'll have 12,000 4 pi times 10 to the minus 9 Henry per centimeter. Our area is going to be 10 by 8. So the stacking factor has nothing to do with mu naught. Mu naught are, let me go to the problem statement here. So we were told very specifically that our core has a permeability of 12,000 mu naught. So that's why we're using mu naught. The stacking factor is only going to show up when we're using a nonlinear material that we are laminating, which this is inherently a linear material because the core is just 12,000 mu naught. We don't have a graph or anything like that associated with it. So realistically, though, the stacking factor only shows up if I'm saying the core isn't solid. It's made of thin sheets of material that are separated by very thin insulating layers. So there's nothing stopping me from saying there's a stacking factor here. There just wasn't one in this particular problem state. All right. Yeah, so we've done these calculations 8,000 times. Let's not bother doing this part anymore. Let's get to the nitty gritty. Okay, so let's say that we have simplified this thing down to the following circuit. So this is RL. This is MMF1. This is R mid. Let's call it middle so that it's differentiated between the thing that I have listed as mid. So this is including the gap. And this is R right, right? This is the flux leaving our coil 1. And this is the flux generated by coil 1 passing coil 2. So phi 1, 2 would be phi 1 times the reluctance of the middle divided by the reluctance of the middle plus the reluctance of the right-hand side, right? So I'm literally just doing current division or flux division here, okay? Phi 1 is just MMF1 divided by the equivalent reluctance seen by the first coil times R middle over R middle plus R right. Okay. We can go one step further and say that MMF1 is just I1 times N1. All right, so that is our flux. Mutual inductance is going to be the flux linkage of coil 2 divided by the current flowing through coil 1. And the flux linkage of coil 2 is just going to be the number of turns in coil 2 times that flux that's passing through it. So that's going to be N1 times N2 times I1 divided by I1 times the equivalent reluctance times R middle divided by R middle plus R right. The I1s cancel each other out. Now the only thing that we need to pay attention to is our directions here. So let me do this one. Yeah, let's do it in red, right? So if we're looking at the flux generated by coil 1, it's going to go in this direction. Some of it's going to branch off and flow through here. The rest of it is going to branch off and flow around this way. And then these guys are going to come together and continue flowing around this path, right? The flux generated by coil 2, which I'll do in this purple color, based on the direction of the winding, is going to go this way. Some of it's going to split up, blah, blah, blah. None of that literally matters. So because the fluxes from both coils are in the same direction, the mutual inductance is going to have a positive sign. If the fluxes were in opposite direction, the mutual inductance would have a negative sign. All of the math is done here. So does that make sense? I know we didn't use any numbers because I didn't want to waste 25 minutes solving the same bullshit equations over and over again. But conceptually, is this okay? Okay. So once we figure out what the flux is, then it's just what portion of the flux generated by the coil passes through the other coil, and then we use flux linkage to smash stuff together. Yes, sir. Um,
Oh, yeah.
Are you, so, sorry, are you saying you want me to provide you an equation sheet, or are you asking if I'm going to allow you?
You mentioned it.
Yeah, so I'm just gonna throw it out there. I don't have the mental bandwidth to make an equation sheet for you guys, but absolutely you're allowed an equation sheet. I'm trying to think of whether or not just allowing you to have open notes would be beneficial or detrimental to you, because it might be overwhelming. And it might also encourage you to not study. So let's say, for this test, I will allow an equation sheet, 1 page, front and back, handwritten, whatever you want to put on there is fair game. So it's not going to hurt my feelings if you put, why are you making that face? No, 1 page of not printed out. So the reason why it can't be a printout is because I don't want you to write a really good equation sheet and just give it to 30 of your peers and allow them to use yours. So it needs to be actually physically handwritten so that it's your work and your work alone. 1 page front and back. Reasonable things like you can't write so small that you need a magnifying glass to see it, you know, all that kind of stuff.